Swayam Prabha. Digital India. Educated India.
Hello everyone. So our new topic is transmission characteristics of textile materials. So here we will discuss the transmission characteristics of air, moisture, liquid in the vapor form, and that water in vapor form and water in liquid form. So that moisture transmission, then heat transmission through textile material. So these are very important not only for apparel textiles but for the technical textiles also. So in apparel textiles, for comfort, proper air transmission should be there, moisture vapor transmission should be there, moisture in vapor form and moisture in liquid form. So during sweating, the air has to travel, fabric has to transport the liquid from one surface to another surface. Similarly, vapor generated within the body has to get transmitted through the fabric, and also heat transmission, our metabolic heat which we generate, it should get transmitted through the fabric. So apart from this apparel textiles, for technical textiles also, like extreme heat or extreme cold climate clothing, where thermal transmission and moisture transmission are also important, and air transmission is also important for technical textiles also, like parachute fabric, where the air transmission, the air permeability of fabric is important. So we will start with air permeability. It is the measure of the air flow through the fabric. So total amount of air flow per unit time, per unit area is expressed as the air permeability. As I have discussed, so apart from apparel comfort, industrial fabric like industrial filter, tents, sailcloths, parachute, air permeability is important. So this is the volume of air passes through a particular area of fabric per unit time. So if we take volume in cubic centimeter cc per second per unit area per centimeter square. So this is the air flow rate, and air flow rate per unit pressure, because if we increase the pressure, air flow rate will increase. So per unit pressure, the total volume of air passes through a fabric of certain area per unit time. So that is the air permeability. Here, if we see this diagram here, the suction pump is sucking the air through this enclosed chamber where the fabric specimen is placed at the center. The fabric specimen is placed here, okay, at the top, and the airflow is measured. Okay, so here also the total airflow is measured here. Air permeability, if we increase the fabric cover factor, air permeability reduces because air flows through the pores, through the spacings between the yarn. Normally, air doesn't flow through the opening in the between the fiber because through the inter yarn space air flows easily. So as we increase the cover factor, the inter yarn space reduces, so air permeability drops. So wave cover factor, if we increase the twist factor, so when we increase the twist factor means keeping all other parameters constant, so yarn becomes thinner and the pore size, that means the spacing between the yarn will increase, so it will result higher air permeability. Now the liquid water transmission through fabric. So liquid water transmission takes place in two stages. First stage is called wetting, that's initial process. Second stage is wicking. So wettability is measured by tensiometry. The tensiometry measures basically the contact angle by indirect method, and goniometry also measures the contact angle, which is direct method of measurement. So goniometry, we can directly measure the contact angle here using the microscopic or video camera. So contact angle between the liquid and fabric is measured by image processing technique. So here the video camera is there, and through the pipette the water droplet is falling on the fabric specimen, and the contact angle here is measured using the video camera, and then through image analysis system we measure the contact angle. So there are two types of goniometry. One is static wetting angle measurement, another is dynamic wetting angle measurement. So in the static wetting angle measurement means when the fabric surface is not absorbing the liquid, that this is stationary, we measure the contact angle, and during the absorption process, when the fabric absorbs, that during the transmission process, how the contact angle is changing, at what rate, that also you can measure using the dynamic system. And the contact angle is related with the surface tension by Young's equation. Okay, so the Young's equation says that contact angle between the solid and vapor equal to, so contact angle, it's a surface tension between solid and vapor equal to the surface tension between solid liquid and surface tension between liquid vapor multiplied by the contact angle. If the contact angle is theta, so we can measure the contact angle. Now here you can see that this is the contact angle theta. Now when the contact angle is very low, contact angle is very low, this is the contact angle theta 1, and here in case of contact angle the fabric, this is the theta 2. The theta 2 is much higher than theta 1. So lower contact angle means there will be wetting, and higher contact angle, that means the wetting is not there. So let us see using the Young's equation how can we measure the contact angles or surface tension. Now this numerical says that a drop of oil is placed on a solid surface and the contact angle is measured as 45 degree. Contact angle is 45 degree. The interfacial tensions are, if we see the diagram, interfacial tensions are given solid gas. Okay, here this is the solid vapor or solid gas, same meaning. SV is 80 millinewton per meter. Okay, and LV, that is LG or V, same, gas or vapor, it's same. So it's 30 and contact angle is 45. What we have to get? We have to get the solid liquid using Young's equation. So Young's equation we know, this is the Young's equation. So what we have to calculate? Solid liquid. So this is given 80. So and this one is also given 30 and contact angle is 45. We solve this numerical. So cos 45 is 0.707 and using this equation we get the contact angle between solid and liquid, surface tension. Surface tension between solid and liquid is this. So surface tension between solid vapor and surface tension in liquid vapor, if it is given, so we can calculate the surface tension between solid liquid by knowing the contact angle. The next numerical similar, it's a water drop is placed on a solid surface. The contact angle is 60. The surface tension solid gas is 72, liquid gas is 50. Then surface interfacial tension between solid and liquid, what will be that value? S gamma SL. Again using the Young's equation, we can get the surface tension as 47.47. Okay. Next is the wicking. So after wetting, when the liquid penetrates within the structure, then it gets some capillary pressure is generated. So when liquid penetrates inside the textile structure, it penetrates. Here the liquid is there, and due to the capillary pressure, the liquid will move along the channel. So that's called wicking. So there are different types of wicking. One is transplanar or transverse wicking, in plane wicking, and vertical wicking or longitudinal wicking. So if you see the fabric, this is the fabric surface. When the fabric surface is horizontal and then the liquid moves in vertical way, so it's across the plane, then we will call it as transplanar. So suppose fabric is vertical and then liquid is moving horizontally, so it has to move across the plane, so which is important for textile material. Suppose a person is sweating and the sweat has to come out from the skin to the outer surface, and this is done through the transplanar wicking, through the thickness. Next is that in plane wicking. In plane wicking means the liquid drop is placed at one particular place and the liquid moves along the plane. Suppose in a body, a particular portion is sweating, because our body, we don't sweat evenly throughout our body. Okay, the sweating is amount of sweats are different depending on the presence of the sweat gland and activity of sweat gland. So in a particular portion, if sweating is there, high sweating is there, then that particular portion will be wet. But due to the in plane wicking, the liquid is spreaded to the larger area, which helps in quick evaporation. So in plane wicking is important, and vertical wicking is also important, where the liquid is moved vertically against the gravity. So here the test method you can see. Here it's a horizontal sintered plate is there, on which we place the fabric, and one light weight is placed on the fabric sample, and at the bottom of the sintered plate means it's porous plate. Okay, at the bottom of the porous plate the water is supplied, and water moves through the porous plate to the top side of the porous plate, which actually simulates the skin sweating, and then the liquid process across the length, and due to the siphoning effect the water is being transported, and the capillary tube, this meniscus, moves from the right to left, and depending on this length we can calculate the amount of liquid being transmitted. Okay. So by the movement of meniscus, so loss in weight of water, so that we can calculate. And vertical wicking is very simple. We place one piece of fabric, rectangular piece, into the water reservoir, okay, and we measure the wicking height. Next is moisture vapor transmission. So details we are not going to discuss here. We will be discussing the analytical part. Detail had been discussed in different courses. So there are different types of standard methods. One is evaporating this method or control this method, then upright cup method, okay, which follows the ASTM method, and here it's a British standard method. Although these two methods are almost similar, only difference is that ASTM method we have to have a strict control over the environment, so that there is no change in evaporation characteristics. But on the other hand, the BS 7209 method, it doesn't talk about the strict control over the environment, but here we have to take one reference material, reference fabric sample we have to take, so that we can calculate the ratio. Inverted cup method, which is used for, and desiccant inverted cup method, which are used for the waterproof type of fabric. So sometimes we need to measure the moisture vapor transmission of waterproof fabric, which is very important, where we don't want any water to come inside, but at the same time the moisture or vapor generated inside our body in the vapor generated within the microclimate has to come out. Desiccant inverted cup method is also there, where we use one desiccant material, okay, which will absorb moisture vapor, and this is also used for the waterproof type fabric. Moisture vapor transmission cell is also there, dynamic moisture permeability cell, and sweating guarded hot plate. These are the methods used for evaluation of moisture vapor transmission. So we are not going to discuss the methods here in detail. So there are different parameters. Okay. So as I have mentioned that evaporative disk method, it gives the water permeability index which with the ratio of the with the reference. But cup method with strict control over the environment, we can actually measure the mass of moisture transmitted through a unit area of fabric per unit time. So it's gram per square meter per day that we can get. Sweating guarded hot plate, we can get the evaporative heat transfer, resistance to the evaporative heat transfer that we can measure. So this is the procedure, BS standard method, where we can calculate the water vapor permeability of fabric at any standard condition. Okay, and then with the reference we can calculate. So of fabric we are calculating water vapor permeability, and with and reference fabric also we can calculate reference fabric. So it's our fabric and it's a reference fabric. The ratio of these two will be expressed as the water vapor permeability index. Okay, and the condition is that we have to test simultaneously the water vapor permeability. Here this method will not give the exact quantity which is getting transmitted, but we will get some, we can at least comparison purpose we can use this parameter. So water vapor permeability is measured per day. So this is the mass of water transmitted in time t. So t hour, if we and with through the area A. So mass of water transmitted is and we can calculate the water vapor permeability index. We can express in terms of percent. So this is the test fabric water vapor permeability and water vapor permeability of reference fabric, and with the reference with the multiplied by 100. So where m is the loss of water in gram through the fabric. So A is the area, T is the time in hour. So we can calculate the water vapor permeability index. Now let us try to do this numerical. During moisture vapor permeability test by evaporative disk method, the initial and final mass of the disk is found to be 220 gram and 119 gram respectively. After 18 hours of test, if the inner diameter of the disk This is after 18 hours of test. Okay. Inner diameter of this is 6.5 centimeter. What will be the water vapor permeability in gram per square meter per hour? It's a very simple. So we calculate the first mass evaporated is 30 gram is the mass evaporated, because the mass of the total dish including water, initially it started with 220 gram, then after 18 hours it becomes 190 grams. So 30 gram water has been transmitted through the fabric. Total test duration 18 hours, and initial inner diameter is 6.5 centimeter. So if it is given, so this is the inner diameter and this is outer diameter of a dish. The dish inner diameter is definitely we have to take, because the what liquid is flowing, water is flowing through the vapor, water in vapor form is flowing through this area only. So we have to calculate the area of this portion. It's 33.18 multiplied by 10 to the minus 4 square meter. So we can calculate the water vapor permeability index using this formula. From the given data, we are getting 502.335 gram per square meter per hour. Next numerical, during water vapor permeability test, a woven fabric, it's a evaporative dish method. Initial and final weight of the dish are found to be 162 and 142 gram respectively, and it's after 6 hours. So in the similar way, the inner diameter is given 20 centimeter. So we can calculate the water vapor transmission rate. To 92.99 gram per square meter per day. So it is asked for permeability per day. So this is per hour, it will be water vapor permeability, and we convert it to per day. Okay. Now upright cup method, which is ASTM, as I have mentioned here, this is actually the difference is that we have to follow the strict environmental norms, which is 23 degrees Celsius, around 50% relative humidity, and 2.8 meter per second air. So we have already seen while discussing the moisture part, moisture and textile part. So relative humidity is extremely important, because for same fabric, if we increase the relative humidity to 75%, the moisture vapor transmission rate will drop, because moisture vapor gets transmitted through the fabric specimen based on the vapor pressure difference. So at this bottom side, the vapor pressure P, which is there, suppose it's a saturated vapor pressure, and at 50% the vapor pressure difference will be more, so the moisture vapor will transmit at a higher rate. But as this is increasing, the vapor relative humidity increases, so moisture vapor transmission will be slower. So that's why here we have to maintain the relative humidity strictly at 50%, then only we can compare. But same fabric if we test at different relative humidity, then the result will be different. Similarly for air flow rate, as air flow rate increases, this will enhance the convective flow. So which will, so still air with zero air flow, the moisture vapor transmission will be slower. That we observe when the air flows, air transmission is there, so it gets, the moisture vapor gets transmitted quickly due to the convection. So to avoid all this effect, so here the air flow rate is also kept constant. Rest other methods are same, but here we don't need any reference method. So directly we can calculate the air flow, that is moisture vapor transmission rate. In earlier method, we have actually we don't use the term gram per square meter per 24 hours. We use the percent, but we can get for a particular condition, and in that condition we can measure the water vapor transmission. This all we have discussed. Now try to do one numerical. Similar numerical is there. During moisture vapor permeability by upright top method, the initial and final masses are 100 gram and 70 gram respectively after 19 hours. So if the diameter of the test fabric is 5.5 centimeter, so diameter of the test fabric is the means the inner diameter of the cup. So same way we can calculate. So this is the water vapor permeability rate 664.84, where the 30 is the weight of moisture vapor transmitted and 19 hours, and this is the 23.75 multiplied by 10 to the power minus 4 is the area in square meter. So we can calculate the water vapor transmission rate. Now thermal transmission characteristics. The thermal transmission characteristics is extremely important and measurement is very difficult. We have seen that in liquid transmission we can channelize the movement. So for any, suppose we want to measure the water flow rate through a pipe, water flow rate through a pipe. So here the pipe diameter, if we know, so if we know the area of the cross section, then we can calculate the flow rate per unit area. Similarly, through air, through the tube, if the air moves in similar fashion, we can measure the air flow rate per unit area. But thermal transmission is very difficult, because if I want to measure the thermal transmission through a plate, the problem here is that this is a plate and I want to measure the thermal transmission. I am hitting here at the back and I want to measure what is the thermal transmission through this fabric or through this material. The heat problem is that controlling the direction of heat is very difficult. Heat will start flowing in all the directions. We cannot channelize the heat. So we'll see how to first channelize the flow of heat. So we use two approaches that I will discuss, and these are the different terms. So insulation value of fabric is measured by thermal resistance, and thermal resistance is reciprocal of thermal conductivity, and thermal conductivity is the unit is watt per Kelvin, is measured by measuring the total heat transmitted through the fabric per unit time with unit temperature difference. Total heat transmitted means through conduction, convection, radiation. And conductivity is due to both fiber and entrapped air. So as the entrapped air content is more, as the air thermal resistance is much higher than the fiber, so conductivity will reduce. And fabric thermal conductivity, the unit is, this is the unit, okay, where that is watt per meter Kelvin. Thermal conductivity unit 1 by R multiplied by D by S, where R is thermal resistance, okay, as it's a reciprocal of thermal conductivity I told. So, and S is the fabric area and D is the thickness. So accordingly the unit gets changed. So as I mentioned, measuring heat transfer in particular direction has a practical difficulty. This complicates the measurement method, and this is overcome by two approaches. One is by comparing with the known sample. So comparison of unknown sample characteristics with a standard sample. So standard sample's conductivity or resistance is known, so we can compare. Another approach is that to reduce the loss in other direction. Suppose we want to measure this is the fabric specimen, we want to measure the heat transmission through the fabric. So what we will do, we will reduce or block the heat transmission sideways and from the bottom. So if we can do it, the block the heat transmission in other direction, we will be able to measure the heat transmission through the fabric. And this is the principle of guarded hot plate that we will discuss. And in the first principle where comparison is done, it's a TOG meter. TOG meter principle is that standard and test samples have to be placed in series. And we know through the thermal resistance, if we know the thermal resistance of individual layer, and if this specimens are kept in series, so from the difference in temperature at different zone, if we record the temperatures of different zones, T1, T2, T3, from there we can calculate the thermal resistance of unknown material when they are kept in a series. Okay. So there are two types of TOG meters. One is two plate TOG meter, but two plates are used apart from the fabric specimen in series, and single plate TOG meter where one single plate, which is reference plate, and another portion is the fabric. This is the reference plate, and here is the fabric specimen. We keep the fabric specimen. This is a single plate TOG meter. Single plate, and if we use another plate here over the fabric, another plate, over the fabric, this will be called two plate TOG meter. And two plate TOG meter, and at the bottom plate is the standard plate of known thermal resistance. Using the standard relationship, here if we know the bottom plate temperature at this point, bottom of the plate T1, and temperature at the junction point, and temperature at the top of the fabric specimen, so T2 and T3. So using standard relationship, we can calculate the resistance of thermal resistance of fabric. Thermal resistance of standard plate is RS. So standard resistance, thermal resistance of fabric we can calculate. Okay. And top plate is used only just to ensure the proper contact is there, and also there is no convective heat loss is there. So the in two plate TOG meter, the sample is placed between heated lower plate, which is reference plate, and insulated upper plate. This is the diagram. The standard top bottom plate, which is, it's called reference plate with a reference resistance, and using standard relationship we can calculate. So where T1 is the temperature, as I have mentioned, T1, T2, T3 are the temperatures of different junction points, and the heater is adjusted so that the upper face of the standard plate is around 35 degrees Celsius. So heater temperature is adjusted in such a fashion. So this T2 value is around 35 degrees Celsius, which is actually close to our skin temperature. Using the standard formula relationship, what is the relationship? The fabric resistance, thermal resistance divided by the temperature difference between the fabric, that is T3 minus T2 minus T3. So R fabric by T2 minus T3, which is the difference between the temperature of two surfaces of fabric, and standard plate with known resistance, and where difference between the two surfaces of the difference in temperature between two surfaces of the plate T1 minus T2. So from this relation, this is standard relationship. So from this relationship we can calculate the fabric resistance, thermal resistance. This R standard should be known, and T1, T2, T3 we can measure. So let us try to solve this numerical. Now here the thermal resistance of a fabric specimen is tested in two plate torque meter with the following temperature values at different locations under steady state condition. So what are the temperature values? At lower part of the bottom plate is 37 degrees Celsius. At the junction point between bottom plate and the fabric is 36.8 degrees Celsius. And at the junction point between the fabric and the top plate is 35.6 degrees Celsius. So we can see the temperature is reducing gradually because of the resistance, thermal resistance. Okay. Now what we have to calculate? The thermal resistance of fabric. Given that the thermal resistance of standard plate is 2 kilo Kelvin per watt. Okay, this is the numerical. So problem is there. So we are using the standard relationship. T1, T2, T3 is given. So as per the relationship of two plate torque meter, we can calculate 2 is the resistance of the fabric, sorry, for the standard plate. So from there we can calculate 12 Kelvin per watt. Okay, which is the thermal resistance of fabric. Similarly, another numerical, only data is changed. Here the standard plate is 1.75 Kelvin per watt, and the temperatures are 37.4, 36.9 and 35.3. Okay, and the calculated value in the same way we will get the fabric specimens thermal resistance is 5.6 Kelvin per watt. And single plate torque meter, here we don't use the top plate. Instead, what we do, we keep the temperature sensor, third temperature sensor, above the fabric specimen certain height, okay, and which measures the air temperature at that height. Okay. Now here T1, T2, T3, T1, T2 and T3 we measure. Where T1, T2 are same as the two plate torque meter, but T3 is the air temperature, that is the room temperature. Here we use the earlier formula initially to get the resistance of the fabric, thermal resistance of fabric, but it includes the thermal resistance of air also. So for that we have to measure the air separately and then subsequently we will subtract. So when to measure the air resistance separately, we remove the fabric, which is called bare plate test, and to get the air resistance using same relationship, so without air we are using without fabric specimen, only by comparing with the standard plate we get the air thermal resistance, where fabric specimen is not there, without a fabric specimen. And then when we test with fabric, we get a thermal resistance with fabric, and if we want to measure the thermal resistance of sample, fabric sample, then we subtract air resistance from it. Our next method is the guarded hot plate. As I have mentioned earlier, in guarded hot plate we directly measure the transmittance of heat, thermal transmittance, where we actually block the heat flow in other direction except the required direction through the fabric. So test plate is surrounded by guard plate in four sides and also surrounded by lower guard plate. So if this is the test plate and one is it's initially this test plate is heated, so initially that there is a cork insulator which will try to block the heat sideways, but it will do to some extent, but to prevent the heat flow completely, so we use guard ring which will be around this side. These are the guard rings. guard ring is also heated. Let me draw in a different color. These are the guard rings. This is guard ring. This is also heated. So the temperature of test plate and temperature of guard ring are kept exactly same. Okay, so that to ensure that there is no heat flow sideway, because there is no thermal gradient. Okay, constant temperature is maintained. So testing as atmosphere is maintained at certain level. This is a schematic diagram. Now, before that, let us see the animation. First animation is that in case of test plate, what is happening? When we heat the test plate, only test plate, nothing is there. So blue color, it's a test plate. Bottom at the lower portion, it's a side view, and the top, it's a top view. Fabric is placed on it. Then it's connected with the power supply. The test plate is connected with the power supply and it's heated, and you can see here the heat is flowing in all the direction. It is flowing through the fabric and as well as through other direction also. So whatever power is being drawn by the test plate is not being utilized to transmit through the fabric. So we cannot measure the exact heat transmitted through the fabric. A portion of the heat is getting transmitted through the fabric. Now, to prevent the heat flow in other direction, let us see this method which we have already discussed. The test plate, and this is the insulating cork, then guard ring. Again we are keeping the cork and bottom plate which is red color, and then fabric is placed on it. Now if we now heat the test plate, guard ring and bottom plate separately to maintain the temperature exactly same, so we will be able to prevent the heat flow in other direction, and only the heat flow through the fabric is recorded and power drawn by the test plate is required, where power drawn is P, and if the area of the test plate is A and at different temperature, Tp is the test plate temperature and Ta is the atmospheric temperature. So from there we can calculate the transmittance, and this transmittance is basically including the air transmittance, so fabric and air. So to eliminate the effect of air, again we have to do the bare plate transmission. So bare plate test we can do, and finally we will get the intrinsic transmittance of fabric U2 by the formula 1 by U2 equal to 1 by U1, which is U1 is basically fabric plus air minus 1 by U bare plate BP, which is actually representing the transmittance of air. So this principle we have already discussed. We are not going to discuss this again. Now if you see the typical values of transmittance, like in glass plate 5.7, well insulated roofs transmittance 0.15, okay, well insulated wall 0.25. These are the transmittance value. So these values, why we are discussing here? Because we want to see with reference to our textile fabric where we are reaching. So textile fabric's transmittance will be much higher than this insulating material. Typical textile material, thick woolen fabric will be around 20 to 80, thinner woven fabric, thick woven and thinner woven 50 to 200, knitted fabric is given. So these are the just reference, and the relationship as we have already discussed. So U1 is the specimen and air, and bare play method we have to test we have to do, and we can calculate the intrinsic transmittance of fabric by this relationship. Now try to solve this numerical. The fabric dimension of the test plate and guard ring, the dimension of test plate and guard ring in a guarded hot plate are given 15 by 15, 15 centimeter by 15 centimeter is the test plate, and guard ring is 50 centimeter by 50 centimeter respectively. So guard ring means this is annular type, where outer dimension is 50 centimeter by 50 centimeter. The power loss from the test plate with and without fabric are given 25 and 50. With fabric the power loss is less. The intrinsic transmittance of fabric is required. Okay, at the equilibrium temperature, and the temperatures are 35 and 20 degrees Celsius. Okay. Test plate and the air. So test plate is 35 degrees Celsius and air temperature is 20 degrees Celsius. So first we have to calculate the area of the test plate. So area of the guard ring is not required. So because we are only concerned about the heat flow through the test plate. So area is calculated. Now in bare plate condition, the power loss is 50. So transmittance of bare plate, so it's the plate also takes certain resistance. So transmittance of bare plate is tested using the formula. 50 is the wattage, area square meter, and this is the temperature difference. Okay, we get the value 148.15. and which is the combined transmittance of fabric. So combined transmittance of fabric means fabric plus the plate transmittance. Combined transmittance is 25 by 0.0225, which is the area, and then temperature difference. So we can calculate the from the which is 74.07, and from this we can calculate the transmittance of the fabric, intrinsic transmittance of the fabric, using the formula given. So the transmittance of the fabric alone is 148.148. This we can calculate. This is 148.15. I think we can check this relationship, this value. It will be 148 because 74 was the combined. So it will be 148.148. Next, dimensions are given. So we'll take the test plate dimension. Here power losses are 20 and 40 given. 20 is the power losses from the test plate with fabric 20 watt and without fabric 40 watt. In the similar way we can do, and temperature differences are 35 and 20. 35 is the test plate temperature and 20 is the air temperature. So using the same process, so bare plate test 118.5 and combined transmittance is 59.15, and fabric transmittance you can calculate using the same relationship, 118.63. Okay. And we have come to the end of this session, and in the next session we will discuss a different topic. Thank you.